All right, so hi, everybody. Today we are finishing up chapter 3. We're going to talk about some specific issues that you may have with chapter 3. The homework for chapter 3 is due this Friday, and then we'll begin chapter 4. And chapter 4 will be the last topic that we're going to have before the midterm exam. So we should be good to go. When we get started with this, do you guys have, before I get started, I guess I should say, do you guys have any questions or anything that you would like me to start covering? Or should I just work some stuff and see where you are? Or do you have a problem that you'd like me to start on? Because I'll pick stuff. I mean, it's not like you have to, but I would rather be directed by you guys if there was anything that you had in mind that you wanted me to do, or any questions that you might have. Okay, well, one thing I'll show you is the last homework problem, number 106. Oh yeah, I did this on a napkin, that's great. But there it is. The work is, yeah, the work is done for 106, or most of it. It's at least set up. And then I have some techniques, some stuff that I did with some of the other problems, including 106. 106 is a complicated problem, so it's not, there's just a lot of parts to it. So I wanted to make sure that you guys had some stuff. But so take a look while you're doing your homework at this file and also at this file, because that would help you get started with that. But anyway, so in the absence of any pointing me in the right direction, I think I'd like to take a look. Probably, I think I'd like to take a look at 71 or 81. Has anyone completed 71 and 81? Just so I'm not wasting anyone's time. All right, so let's take a look at that. So what we're talking about in this section is we're talking about those moments. So there's a little bit of stuff here that I want to talk to you about. We've talked about moments being taken about a point, how a moment is always, it has to be taken about something because you're talking about something that is rotating. Now, this part, this piece of the math is talking about the moment taken about an axis. And an example of what we're doing here is if you have like a trunk, and there are hinges on the trunk, okay, or a storage, as a foot locker or anything like that. The trunk lid is going to open on the ledge with the hinge, right? So in other words, we're really concerned about finding how much of the moment of force acting through a distance is going to apply on that axis. And that's really what this mathematical piece allows you to compute. So instead of taking about a point where you're talking about something spinning about a point, you're talking about something that's rotating about an axis. Now, they do all kinds of interesting and less than practical things about rotating on an axis, but that is a practical application. So what we're talking about then, if you look at the symbology, first of all, it says M sub BL is equal to then some lambda terms, some XYZ terms, and some F terms, right? So basically what we're talking about, if you look at this diagram, BL is the axis here, okay? And what they're saying is, if you apply a force at point A that has a magnitude of F, what piece of that is going to create a rotation about the axis that goes through point B and point L? So in order to do that, you need to find three vectors, and then we will set up a determinant of that, of those three vectors. The first are lambdas along BL, all right? So in other words, the first row of the determinant, you find the vector BL, whatever that is, then you find the length, and then you determine the unit vector or the vector in that direction that has a length of 1. And those would be the top row of your determinant. The second row, it says x a sub b, y a sub b, and z a sub b. What that means is that if you take a point on the line of action of the force, which the easiest point for us to find on the line of action of this force F would be A, because A is defined by something in the spatial coordinate system. The vector x, y, and z, the second row of that determinant, is going to be the vector that goes from point A to point B. In other words, from the line of action of the force F to the line that we're taking the moment about. And then last but not least, we just have the components of the force F. Now, I just want to work one of these out with you, but basically it works out the same way as when we did the 3x3 determinant, where we did the slashes multiplied together, minus the slashes multiplied together. So the only difference is that a moment projected onto an axis, once again, does not have enough directional property to be a vector. It turns out that projection is in fact a scalar. So this is something, like I told you last time, has always kind of bothered me, because it seems like you have something that has a magnitude and a direction that it should be a vector, but mathematically the direction properties are not sufficient to make it a vector. So the answer that you get is a scalar directed along the axis B sub L, right? So let's take a look let's write this down first of all. And let's see, I want to see, there it is right there. Okay, this is the governing equation, is that the moment along B sub L is equal to lambda dotted with M sub B, which is equal to lambda dotted with R, which is that moment arm from A to B, crossed with the vector F. And this lambda is the unit vector along the axis of rotation. In this case, the way we have it written, B sub L. So you can see mathematically that because this is a dot product, that this is going to be a vector dotted with a vector, which yields a scalar. So there's a mathematical reason for the fact that this is not in fact a vector. But the solution that you use with the determinant is basically identical, except that at the end, you don't keep things separated out into coordinates, into directions. You just add them all together or subtract them, and you get a value. All right. So for example, just really quickly take a look at this. We have a cube, and we have a force acting from point F to point P. And we want to determine the moment of P about, it says about point A, about the edge AB, and then about the diagonal AG. Well, let's take a look at AB. All right, if we want to get that, if that's going to be the axis, so in other words, the hinge, if we were looking for a practical idea, would be right here at AB. If you think about A sub B in coordinates, here's X and Y in the plane of the paper, and then Z coming out. A to B does not have a Z component, does it? Because it's flat, it's flush, it's not in the page of the paper, but it's parallel to the line of the paper. So that means that this is just A sub B is going to have some dimension in the X direction only. So in other words, there's not even a direct, it's horizontal. So all this is going to be, the vector A sub B is just going to be 1i, right? Because it just has an I component. All right. So if we look about it that way, we can then, well, they do it a little bit differently. They break out the moment. They say, here's P, which is the force. And then the moment arm is gonna be anything from this axis to this point. And they chose F to A, which, yeah, that's fine, that'll work. I might choose just F to B, but that's okay. F to A works as well. So they just, this is your moment arm, okay? And so they just break that down, and what is that gonna be? Well, it's gonna be 1x, 1i, minus 1j, because it's a unit cube. And then you have the force. So they do that cross product, and then they dot it with the unit vector from A to B, which is just 1i, and then they come out with this value. And as you see, my I, J, and K components go away because it's just a value at that point. All right. I just think if there's anything of interest here. In general, the solving problem on your own section are very, very helpful to make things work like that. Let's see what we have here. Like 71. Oh, this is gonna be a force coupled system. I really wanted to get one here. Oh, I like this trunk problem. I like 50 and 51. Did I assign those? Let's find out if I did or not. $57, $40, $57. All right, let's see what we have. Oh, 57 will do. All right, so has anyone done 57? Okay, good deal. So I'll set this up for you. And problem 357 says we have a frame, ACD, which is just this steel structure here that's mounted in the wall at point A and point D. And it is hinged at A and D and supported by a cable that passes through the ring at B. Okay, so this is a cable that passes through the ring. One of the things that tells us is because it's not two separate cables, it's not knotted off on either direction, it has to have the same magnitude because it's the same cable. So the magnitude of the tension in those two cables is going to be the same. Obviously not the direction or the vector, but the tension, the magnitude will be the same. Knowing that the tension in the cable is 450 newtons, determine the moment about the diagonal AD of the force exerted on the frame by portion BH of the cable. All right, so what we have is, we have a few different things. We know that our moment, I better put this back up. Hang on, this is where I have to keep sharing and unsharing. All right, so in this case, for problem 57, we need lambda along the diagonal, which is AD, okay, to begin with. Then my moment arm, let's just do it the way they do it too. We'll just take a look at this. My F, my force, is going to be, let's see, the force is going to be the vector tension, or let's say the tension in BH times lambda along BH, right? And then last but not least, my R vector is going to be from the moment, we're going to take that moment about some point. Let's see, did I ever get that? So I need to get, here's my force, and here's my cable. All right, I would just, there's a bunch of different choices you could use for your, the moment arm. But if I take it about B, Do you see what that will do is if I just say that my moment arm is from anything on any point of action, any point on the line of action, BH, if I choose point B going over to where the force is applied at point C, I could just say that R then will be equal to the vector BC. All right. And that should make things a little bit easier. All right. There. All right, so this is what we're looking at. So we need to get lambda, which is going to be lambda along AD. And we need to get RAB, which is just the vector BC, and we need to get the force, which is the tension times this. So if we go back, we're going to have some things that we need to work out based on those locations. There you are. All right, let's take a look at that. Okay, so first of all, let's just start with the vector B to C, which is my R. B to C extends in the X direction, and it goes from 0.5 meters to 1 meter. So the entire vector BC can just be expressed as 0.5 meters in the I direction. Okay. Looking at our lambda along AD, let's find our vector AD first of all. Oh, wait a second. Yeah, that's not going to work because that doesn't coincide. I was thinking that the diagonal was here at B, but it's not. So I need to have something that passes through both. So let me think about this a second. Let me read through the problem one more time. Is hinged at A and D, tension in this cable, determine the moment about the diagonal of the force exerted on the frame. Okay, so let's just go from C to D for our vector instead, because that is on that vector AD, right? So let's say that R is going to be C to D. And that goes back into the page. So it's in the Z direction. And since it goes into the page, it's negative. So that is negative 0.75 meters in the K direction. Right? I'll just show you my correction here. Right there. All right, so going back to the screen. Let's see. All right, so we have R. This is not going to be, it's not going to, the lambda along AD is correct. And then my R AB, I've got that. So now I have to find my force. All right, let's look at A to D first of all. What is the vector from A to D? Well, if you think about it, in the X direction from A to D, the distance is 1 meter. So that's 1 meter in the I direction. And there's no component in the Y direction because it's horizontal. So it's plus 0 meters in the J direction. And then in the K direction, it goes back into the page, 0.75. So it's negative 0.75 meters in the K direction. All right. So the first thing I need to do is to find the unit vector along AD. So I have to find the length of AD, which is the square root of 1 squared plus 0.75 squared. Anyone have a number for me? So if I take the square root of that, oops. All right, so my sum is 1.56. And so if I take the square root of that, 1.5625, that gives me 1.25 meters. All right, so that means that lambda along AD is going to be 1 over 1.25 I minus 0.75 over 1.25 K, and it's 0 in the J direction. So there, I have one of the vectors that I need for my determinant. My R, I also have that vector, right? So now I need to find my force vector, not the magnitude. But I am told in the problem, let me share this again, that the magnitude of the tension is 450 K. Or 450 newtons, pardon me. All right. But I need to find then lambda along that vector BH. All right, so in order to do that, I need to write the vector BH out first. And if I look at where I am, going from B to H, in the X direction, it's 0.5 meters. So it's 0.5 meters I. In the J direction, it's flat, so it's 0 meters J. And in the K direction, it goes back into the page, 0.75 meters. So it's a negative 0.75 meters. Now I'm going B to H. Sorry, I got confused. I was looking at my floor. B to H goes up to that support. So from B to H, all right. First of all, this is a little bit more complicated, but it's okay. B is at 0.5 meters in the X direction. H is at 0.875 meters. So that means that in the X direction, it's 0.875 minus 0.5 meters, right? In other words, the distance from B to H extends to the right, which is positive by 0.375 meters. In the Y direction, we go all the way up 0.75 meters, so that's also positive. And in the Z direction, B to H goes back into the board or back into the wall, negative 0.75 meters K. All right. So this is my B sub H vector. To rewrite a little bit more clearly, this would be 0.375 meters I plus 0.75 meters J minus 0.75 meters K. All right, so to find my unit vector then, I need to find the length of that vector. So once again, 0.375 squared plus 0.75 squared plus 0.75 squared. And the length is and then 0.75 squared is 0.5625, and again 0.5625. And then if I add to that, we're going to get a total of 1.265625. And if I take the square root of that, that is the length of B sub H then is 1.125 meters. Right. So then lambda BH, let's just do it all in one. F then is going to be 450 newtons times the unit vector, 0.375 over 1.125 I. Units are gone because meters cancels meters, plus 0.75 over 1.125 J minus 0.75 over 1.125 K.
All right, and then I would distribute the 450 through and simplify those values. So the next thing I want to go is back to that governing equation that says the moment about an axis, the projection of a moment onto an axis is equal to lambda dotted with R a sub b crossed with F. Okay. And now I have all three of those vectors. So I write that down one more time, equals my components of lambda. Is right here. 1/1.250 and negative 0.75 over 1.25. The second row is my R, the distance from the force to the line of action or to a particular point. And that is negative 0.75 meters K. So it's 0, 0, negative 0.75 meters. And then the last one is the force. I can put 450 outside, but let me just do this. I'm just going to simplify this. So if I take this 450, multiply it by 0.375 and divide that by 1.125, this number turns out to be 150, and my units are going to be newtons. The next number, 0.375, is half of that. So this is double. That's just 300 newtons minus 300 newtons. All right. And now I have my determinant ready to set up. Yep. All right. So how do I do that? Well, I duplicate my first two columns. And I have lots of zeros, which is really super duper because that makes for lots of things multiplied by 0. So things turn into 0. So then I can say the moment BL, or the moment about that axis AD from this force, it's going to be this multiplied together. But since there's a 0, that's 0. And it's going to be this, which once again is 0. What's that?
0 again.
0 again. That's right. 0, 0, and 0. So what do you get? Equals 0. Exactly right. So,
Wait, no, yeah. Yeah.
oh, did I miss one? I was just getting excited is what you're telling me.
The 1/1.25, 0.75.
Oh, yeah. Thank you. There it is. Thank you, guys. I was excited for a minute there, but I thought it's not really true. I was going to write the picture and say, yeah, I don't think I got that one right. So, huh. But that's the first one. You think it's
The second.
The second one going from
Directly.
right here?
Yeah.
Yeah, there you go. Thank you. So that would be a negative because we're going that way. Negative 0.75 meters and a positive 300 newtons. Okay.
Why is it a negative?
Because the slashes that go this way from left to right are you add them and then you subtract them the other way. But what you find then is that you have a negative and a negative. So the whole thing turns out to be a positive, right? All right. So that means at the moment, and this is actually going to be about that. Yep.
The newtons were originally negative, right? No, positive.
No, right. So this was negative and this, and then the whole thing is negative. So the overall expression is going to be a positive. All right. So we're taking the moment about AD. So you can then say the moment, that projection about AD is equal to if I take 0.75 and multiply it by 300, and then divide that number by 1.25, I get 180. And the units are Newton meters, which is a good unit for a moment.
Wait, how did you? If we have like the moment of BL. then
Yes.
we could create the 80.
Oh, okay, that's a great question, Caitlin. What I did was, I just started with this original, the origin equation, which said BL, right? But in our work together, BL is actually, they're just using it as a placeholder, but here it would be AD. In other words, there's not a vector BL that we're working with. BL was just in the original equation. Ah, the vector that you're taking, the first one, in this case, AD, is the axis that you're taking the moment about. The force is just the force, whatever that happens to be. And then the R value is something from the line of action of the force to, and you know what, I did something wrong here too. I used P. So, or let me look at my R. Did I do it correct? You have to hang on just a second. Yeah, I messed up on that one too, because I started using this P, but I need something from, so here's my force, which is in V sub H, right? Here's my axis from A to D. So I need something that goes from somewhere on here to somewhere on here. So in this case, I could use B to D, which would be the easiest one, 0.5 minus 0.75. That would be a good R value. R being that moment arm vector. Okay. So let me think if I can explain this. I'm going to write this out. I see the question mark, so I'm going to try one more time. And then let's see if I can explain this. Okay. Let's go back to this. Okay. When you compute the projection of a moment onto an axis, you need 3 vectors. The first one you need is lambda, the unit vector, along the axis. The second one is R, which is from the line of action. No, it's not, it's the opposite. It's from the axis to the line of action of the force. And third, you need F, which is the force. All right. So in this case, let's see what that means. I'm not going to draw the whole drawing out, but this is what I'm going to do. This is A to D. And the problem tells us that we want to take the moment about AD. So this is the first one. The first vector we need is lambda on AD. Okay, now here, B starts here and ends up here. This is B to H. And we know that the force is the tension written as a vector, not as a scalar, along B sub H. So that's this right here. Then the last thing we need is R. And R is the connecting piece between the force and the axis. So in other words, we need to find a vector that goes from point B to somewhere along the line of action on here. And it could be any of those things. So we have to decide we're going to go from point B to somewhere on AD. Okay? And I said, I would like to go from B to point D because it's easy for me to pick up the dimensions. Not easy enough because I picked up the wrong force. So therefore I had the wrong R. But it would be B to D would go 0.5 meters in the X direction and negative 0.75 meters in the K direction. So to go back and correct that piece of it, this is correct. And this is correct. But this, oops, you need to see this big, sorry. Okay, so on my work here, this is correct. This is my F. It's going to go into the determinant. This is correct. This is lambda along vector AD. But this is not correct because I just went, what I did was in my haste to write it down, I just looked at this force P and I thought that for a moment, I just thought that was the force that I was working with was P, but it's not, it's this one, right? So that means my R value is going to be 0.5 because I have to go from B to D, or I could go from B to A, I could go from B to anywhere, but I just chose B to D. So that would be 0.5 minus 0.75. So my actual R value would be the vector BD, which would be 0.5 meters I minus 0.75 meters K. All right. So now with that, I'm going to go back and correct my work. All right. So on this determinant, the only thing I would have wrong would be that there would be a 0.5 here. And this is still 0. So in other words, the middle row has to match this. This is my middle row. So I have to do that. That means that this one's going to be 0.5 as well. All right. All right, so I'm going to rewrite my determinant because it's ugly, but we could just call this, let's not go back to the original. Let's just call it what it is. It's the moment, the projection of the moment about the axis AD. So if I put my numbers into the determinant properly, I would have 1 over 1.25, 0, negative 0.75 over 1.25. Then in my second row, I'm going to have 0.5, 0, negative 0.75, and those are meters. Top row is a unit vector, so there's no units on that. My bottom row is 150 newtons, 300 newtons, negative 300 newtons. All right, so then to execute that math, I write this first 2 columns again. Okay, and now I'm going to do 1, which is 0, 2, which is 0, and 3, which is not 0. So the first term I have that is non-zero is negative 0.75 over 1.25 times 0.5 meters times 300 newtons. And now I go the opposite way from lower left to upper right. That one is 0. This one is not 0. But it's minus because of the direction of travel, 300 newtons times minus 0.75 meters times 1/1.25. And then last but not least, I have another 0 term. All right. So then if I do the math on that, here I get 0.75 times 0.5 times 300 divided by 1.25. And my first term turns out to be a negative 90 Newton meters. And my second term, I have a negative times a negative. So that's going to be a positive. The value is 300 times 0.75 times or divided by 1.25, 180 Newton meters. And the answer then is a positive 90 Newton meters, which I think is numerically what I came out with before doing it the wrong way, but that's just a horrible coincidence, so. So it takes a little bit of thought. It takes a lot, and it's really important when you find especially that R value, because the axis is a prescribed vector and the force is a prescribed vector. But the R value that you use that connects the two, you have some different choices, and you can make it easy on yourself or hard on yourself. And as we could see in this, the more zeros that you have in your determinant, the easier the math is going to be. So you can choose it to give yourself a little advantage. Yes,
So obviously, the math would be good as far as you do, I can keep it with it, but it says in the book that it's a negative.
it could be. It would mean that I have a sign somewhere wrong.
I'm just curious.
Yes.
Because you flip it, when you do the diagonal this way, you flip the sign.
Yes. Well, okay. So it could, you know what, there's a bunch of things I could have done wrong. I could have chosen my R value backward. Okay. I could have chosen my force incorrect. I could have gotten it backward. I mean, I should go from B to H. Yes.
Would it be the, it's like the AD. it's
Yes.
here, and it's supposed to be one. There's supposed to be 0.9.
From A to D. From A to D, it should be 1, right? Because here's A and here's D. So it should be 1 in the X direction minus 0.75 in the Z direction. Yeah,
You like when you're doing the multiplying cross.
did I have it, you mean in the multiplication or in the actual finding of the vector?
I was thinking.
Yeah, no, my feeling is I have an arithmetic mistake somewhere. So, which is another reason why when you do these, lay it out really explicitly, because if you make an arithmetic mistake, you should not lose very much credit.
There's no coolness.
Yeah, oh, I know, so we have to, yeah,
What are each, with your, whatever those are.
permanent,
Yeah, what are each line?
okay,
What are each?
those are called rows.
I know, but like, what are they?
What do they call, what do they represent? Okay, good question. Let's see. Okay, so if we go back and we look at this, so we're saying the moment about some axis. Sorry? Oh yeah, you probably want to see this, don't ya? Okay, there we go. The moment about some axis, the projection, and this is a scalar, right? Is going to equal the determinant found by finding 3 rows. This is the first row is the unit vector along the axis. Okay, so we call that, in this case, lambda ADX, lambda ADY, and lambda ADZ. The middle row, which is R sub X, R sub Y, R sub Z, is the moment arm between the, let's do this, a point on the axis and the force. And the final one, F sub F, X sub Y, and F sub Z, is the force. So really the newest piece of this is finding this value of R, isn't it? Okay, so like on this problem, here's my force, right? My force is along V sub H. My axis is along A sub D. So what is R? It's something from the force to the axis. So in this case, I chose point B to point D. So it's a distance, it's a vector. It is a line that you could take if you had a string and put on the force and then bring it over to the axis that you're taking the moment about. Okay. Is that helpful, Caitlin? Okay. I'm trying to think of another way to explain it to you.
So we're not worried about P at all. Right now we're with the P.
Right, it's just asking us about BH. We could do this exact same thing with P.
What exactly is the moment?
A moment is something that tends to cause a rotation. So in this case, if you remember at the beginning of class, I talked about like if you have a foot locker or a trunk, if you push or pull on the foot locker's lid, no matter where you pull or push, the only place it's going to rotate is on the hinge. That's the axis of rotation. Okay, so the force that you pull out or push on the trunk lid with would be force. And then the R would be some distance from where you're pushing to the hinge. And in this case, it would be some line along the top of the lid. So the other thing to think about this is you're going to have forces that are more effective in creating that hinge effect than rotate the trunk. So if you really want to open the trunk, your best bet would be to just lift it, right? If you push on it straight on, you're never going to get a moment. It's just going to push the trunk. If you want that hinge to rotate, you're going to have some component of it that tries to lift the lid. So that's what they're finding. So like if you do this force that looks like this, and you want to get that rotation about that hinge, how much of a moment are you get? The bigger the moment, the more likely it is to rotate. Now Joyce pointed and said negative or positive. What does that mean? Well, the thing about the hinge lid again, right? If I have one direction, one is going to lift it up. If I have one direction, one is not going to lift it up at all. It's going to push it down. That's not really good. So you're really looking at what an effective motion is, or in the cases of something sitting still, what you need to oppose it with to keep it from rotating. All right? Yes.
So in the case of this question,
Yes.
the axis would be point D technically. It's a fixed point.
The axis is from A to D. Yeah, absolutely. That's the new piece of this, really, is that we're talking about that axis instead of a point. So what's a point? Do you remember when I talked about teeter-totters? Okay, you have two kids on a teeter-totter, there's a pivot point, okay? When you have a trunk lid, you have a pivoting axis. And I see my colleagues are peeking in the door, so anyway, let me stop the recording.